Alright, let's dive into finding the Fourier transform of a very special function, the Dirac delta function. So the problem we want to solve is how do we find the Fourier transform of the Dirac delta function, which we write as delta of x. Just to quickly remind ourselves, the Fourier transform of a function f of x, which we denote as f hat of k or f of fx of k, is defined by this integral here. It's the integral from minus infinity to infinity of f of x multiplied by e to the power of minus iota kx, and then we integrate with respect to x. Here, x is our spatial variable and k is often thought of as the wave number variable. Now, before we calculate the transform, let's remember what the Dirac delta function actually is. The Dirac delta function delta of x is defined by a particular property. This property tells us that for any continuous function you might have, let's call it phi of x, if you integrate phi of x multiplied by delta of x minus a over the entire real line, the result is simply the value of the function phi evaluated at the point a. Specifically, and this is the case we'll use most often, when a is 0, the property simplifies the integral from minus infinity to infinity of phi of x multiplied by delta of x dx is just the value of phi evaluated at 0, which is phi of 0. Okay, so with that definition in mind, let's set up the Fourier transform integral for the Dirac delta function. We simply substitute delta of x into the definition of the Fourier transform we saw earlier. This gives us the integral shown on the slide. Now the magic happens when we evaluate this integral. We use that key property of the Dirac delta function we just discussed. The integral from minus infinity to infinity of phi of x times delta of x dx is equal to phi of 0. In our specific integral, which is the integral from minus infinity to infinity of delta of x times e to the power of minus iota kx dx, the function phi of x that's being multiplied by delta of x is this term here, e to the power of minus iota kx. According to the delta function's property, this integral simply evaluates to phi of 0. So we just need to figure out what phi of 0 is when phi of x is e to the power of minus iota kx. We substitute 0 for x, giving us e to the power of minus iota k times 0. Well, anything to the power of 0 is just 1. So phi of 0 equals e to the power of 0, which equals 1. And there you have it. Putting it all together, the Fourier transform of the Dirac delta function, delta of x is f hat of delta of k, which is f of delta x of k is equal to 1. So the Fourier transform of the Dirac delta function, which is a function sharply peaked at x equals 0 in the spatial domain, becomes a constant function with a value of 1 across all values of k in the wave number domain. Pretty neat, right?